Okay. Today we will discuss about Lagrange method of undetermined multipliers. Lagrange method of undetermined multipliers. Undetermined multipliers. So we have some undetermined multiplier, that is lambda, mu, etc. So we have to calculate the value of multipliers also. So we have the function. So we consider that let f x y z be the function and this is connected by a relation. तो ये ध्यान रखना होगा कि this function, this is our basic function f x y z connected by a relation to the function phi of x y z is equal to 0. Okay, so we make two functions. First function is already given. Second function, which is connected by the relation, so that means phi of x y z equal to 0. So make Lagrange function L. L is equal to f plus lambda phi. The function f, which is connected by only single relation, that is phi. So we use only one Lagrange multiplier, that is called lambda. If a function of fx, yz, which is connected more than one functions, so we use two multipliers. Okay, we use two multipliers. Suppose if a function x, y, z be connected by a relation to the functions phi1 xyz and phi2 xyz. So then you write down the Lagrange function L is equal to f plus lambda into phi1 or plus mu into phi2. So here lambda and mu work as a multiplier, undetermined multiplier. So lambda be the undetermined multiplier at this stage. Okay, so we also determine this value of lambda. So now this is our equation 1. We see that the function f is also function of x, y, z and phi is also function of x, y, z. So differentiate 1 partially with respect to x, y and z. So we get del L upon del x is equal to del f upon del x plus lambda del phi upon del x. When we differentiate with respect to x, we differentiate with respect to y. The del L upon del y is equal to del f upon del y plus lambda del phi upon del y, and del L upon del z is equal to del f upon del z plus lambda del phi upon del z. Okay, so now finding the stationary value. Stationary values, we put del L upon del x is equal to del L upon del y is equal to del L upon del z equal to 0. When we put this equal to 0, so we get del f upon del x plus lambda del f upon del phi upon del x equal to 0. So this is the equation number 2. Del f upon del y plus lambda del phi upon del y is equal to 0. This is equation number 3. Del f upon del z plus lambda del phi upon del z equal to 0. This is equation number 4. So we have 3 equations here. So on solving above equations to find the value of x, y, z and lambda. So x, y, z be the stationary values. Okay. So we do same thing in each question as per the given statement. Now we start the first question related to Lagrange method. So first question is that the statement of the question, find the point upon the plane ax plus by plus cz is equal to p at which the function f equal to x square plus y square plus z square. So the main function f is given, the has a minimum value and find its minimum value. Okay, so when we are going to find the minimum value of f, so f is our first function, primary function. So this we can write down as given that f is equal to x square plus y square plus z square connected by the relation So that means the plane is connected to this. So that is the second function, ax plus by plus cz is equal to p. So now we consider this as function phi, second function. Second phi, so this equal to ax plus by plus cz minus p. So this is our second equation, and we make the Lagrange function. So Lagrange function, that means del, first we calculate the value of f plus one multiplier, because one function is given. So this equal to x square plus y square plus z square plus lambda ax plus by plus cz minus p. So this is our L. Now we differentiate this with respect to x, y, and z. So this is equation number 3. So we write down the differentiate 3 partially with respect to x, y, z. So del L upon del x is equal to 2x plus lambda a. We directly put as equal to 0. And the second del L upon del y is equal to 2y plus lambda b equal to 0. And del L upon del z is equal to 2z plus lambda c is equal to 0 for finding stationary values. So here we write down from this equation. So 2x plus lambda a equal to 0. So this gives us x equal to lambda a upon 2. So we have the value of x from equation number second. So we have y equal to minus lambda b upon 2. And from third one, we have z equal to minus lambda c upon 2. So the value of x, we have minus lambda a upon 2, lambda b upon 2, and lambda c upon 2. Now we have one undetermined multiplier, that is lambda. So we need to calculate the value of lambda also. So we put this into the given function, given relation. So we see that the given relation is ax plus by plus cz is equal to p. So putting the value of x, y, and z in above equation. So x means lambda a upon 2 plus by minus lambda b upon 2 plus cz minus lambda c upon 2 is equal to p. So here we see that minus lambda we can take as common from all three terms. So first term you can write down as a square upon 2 plus b square upon 2 plus c square upon 2 is equal to p. So we also taken common as 2. So we write down as a square plus b square plus c square is equal to p. So you can calculate the value of lambda directly. So what is the value of lambda? So value of lambda equal to minus 2p upon a square plus b square plus c square. So we have calculated lambda, undetermined multiplier, that is lambda. So we have calculated lambda. So the value of lambda is minus 2p upon a square plus b square plus c square. Now, on the basis of this lambda, we also calculate the value of x, y, and z. So the value of x equal to, we have minus lambda a upon 2, minus lambda a upon 2. So we put the value of lambda in this equation. So we see that so minus minus is plus, and this gives us 2pa upon 2 into a square plus b square plus c square. So 2 cancel, minus minus we can add plus. So this gives us ap upon a square plus b square plus c square, and y equal to minus lambda b upon 2. So this equal to 2pb upon 2 into a square plus b square plus c square. So 2 cancel. So this bp upon a square plus b square plus c square. And similarly, we write down the z equal to minus lambda c upon 2. So plus 2 uh, pc upon 2 into a square plus b square plus c square. So this gives us cp upon a square plus b square plus c square. So these are the stationary values. So stationary values you can write down as x comma y comma z. So this can be written as ap upon a square plus b square plus c square, bp upon a square plus b square plus c square, cp upon a square plus b square plus c square. So after calculating the stationary value and Lagrange multiplier lambda, we calculate the minimum value of function. So the minimum value . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . minimum value of function f is equal to, so function having value a square x square plus y square plus z square. So we put the value of x, y, and z in this function. So we see that this gives us a square p square upon a square plus b square plus c square to the whole square, b square p square upon a square plus b square plus c square to the whole square, plus c square p square upon a square plus b square plus c square to the whole square. So we can take common a square plus LCM to the whole square. So we write down as a square p square plus b square p square plus c square p square. So this equal to p square we can take common. So gives us a square plus b square plus c square upon a square plus b square plus c square to the whole square. So this to this cancelled. So value of the function, minimum value of the function is f equal to p square upon a square plus b square plus c square. So this is our answer. Okay, so hope you understand this question related to Lagrange function. That means Lagrange multiplier. So we add some multipliers, that is lambda or mu as per given the statement. So that means the number of relation is given. When only one relation is given, so we use one multiplier. More than one relation is given, so we use the multiplier accordingly. Okay, so we take next problem related to Lagrange multiplier. The next problem is that show that the rectangular solid of maximum volume that can be inscribed in a sphere is a cube. So first we understand the statement of the problem. This say that rectangular solid of maximum volume that can be inscribed in the sphere. So sphere means we have a three-dimensional shape, that is x square plus y square plus z square equal to r square, whose center is origin. So we just consider that. So that means we can understand through a figure. So this is our sphere, and we take the axis. So this is origin. We consider this as the y-axis, this is z-axis, and this is our x-axis, and a rectangular solid that can be inscribed in the sphere. So this is a rectangular solid. So we understand that the length, breadth, and height of a rectangular solid is 2x, 2y, 2z respectively, and assume that r be the radius of a sphere. So then the equation of a sphere, x square plus y square plus z square equal to r square. So here we consider center is origin. So this is our first equation. Okay. Uh, and first equation is volume of a rectangular solid. So volume of solid is equal to L into B into H. 2x into 2y into 2z is equal to 8xyz. Okay, so this is our first equation. So that means volume of a solid that is inscribed into the sphere. So this is function f. F is equal to 8xyz, and function phi is equal to x square plus y square plus z square minus r square. So we are calculating that a rectangular solid of maximum volume that inscribed in the sphere is a cube. So first equation is f equal to 8xyz. That means volume of the rectangular solid, and function phi is that. So we make the Lagrange function. So L equal to f plus lambda phi. So we write down as L equal to 8xyz plus lambda into x square plus y square plus z square minus r square. So differentiating 1 with respect to x, y, and z, and putting del L upon del x equal to del L upon del y equal to del L upon del z equal to 0. So del L upon del x is equal to 8yz plus lambda into 2x equal to 0. Del L upon del y is equal to 8xz plus lambda into 2y equal to 0. Third one is del L upon del z is equal to 8xy plus lambda into 2z equal to 0. So when we solve this equation, so we get 2 lambda x, 2 lambda x is equal to minus 8yz, and from this equation 2 lambda y is equal to minus 8xz. From this equation 2 lambda z is equal to minus 8. This is 8xz. This is 8xz, and this is 8xy. So we can give this as equation number 2, this as equation number 3, this as equation number 4. So multiply 2, 3, and 4 by x, y, and z respectively. So when we multiply equation 2 by x, so this gives us 2 lambda into x square equal to minus 8xyz. Second equation 2 lambda y square is equal to minus 8xyz. Third equation 2 lambda z square is equal to minus 8xyz. So from these three equations, you can see that all LHS part is equal to the RHS part. That means minus 8xyz, minus 8xyz. So this means that uh, 2 lambda x square is equal to 2 lambda y square is equal to 2 lambda z square. So this gives us x square equal to y square equal to z square. So x square is equal to y square equal to z square. X square is equal to y square is equal to z square. So this can be written as x equal to y equal to z. So x equal to y equal to z when all are equal. So that means that is not a rectangular solid, that is a cube. So hence we can say that A rectangular solid is a cube. So that means x is equal to y equal to z. So that rectangular solid is a cube.